Okay, let's get started again. So we have studied this very interesting class of models. They are very simple in terms of the loss function. It's just like least squares, but the model is a bit more powerful than the linear models we've seen in the past, right? In the past we have seen, maybe we have taken our parameter and then multiplied it with a constant. That's a linear model, right? So if you multiply a parameter vector with a fixed data matrix. But what's different here is that we multiply two parameter vectors. That's why the function is a bit more powerful and a bit more strange. So that it's actually turns out to be a non-convex function. So again, matrix factorizations, they are all the problems which are of this form. So an interesting special case is also when f is so when you have all the entries, right? There's nothing unobserved. So omega is all entries. That's just a special case. Okay, let me write. If omega is all entries, that's an interesting case. Of course, it's also an important case. And then what you get is something you have seen already. So namely, then you will just sum up all the squared entries of the difference of x and the product. So it's the norm squared, but this is a matrix, these differences. So this is the Frobenius norm, which you have seen in k-means. So that's exactly what you had in k-means, trying to find the best w and z, but there actually we had a constraint for z, such that they fit at x, but there we cared about the fit everywhere. There was no distinction of observed entries or not. And there is a small notation thing in k-means. We actually use the transpose to approximate the data. So we use X transpose. But here we don't care. So here we don't have data points. So we can use anything we like. So whatever was called X transpose in k-means, because there it had a meaning, it was data points, each column. Now we're just looking at the X as any matrix, and we care about individual entries. That's why we just write it as f of wz, and you can use this to approximate any x you like. Just a notation. Okay, so this Frobenius case is interesting. So if you minimize over without any constraints, just what's the best w and z here to approximate the x everywhere, that actually has a closed form solution. So for a fixed k, this can be solved in closed form, and that's actually by the SVD. So this is asking, what's the best rank k approximation to x? And I will care about all the entries. So that's actually what you're going to see next week, when we will discuss this a bit in more detail, but probably many of you have already seen SVD. So this is one of the nice properties of SVD, that it solves this problem for the special case when omega is the full entry set. And so yeah, you can think that it's not a big deal if I care about all the entries or only some of them, but it actually is a very big deal. So yeah, if you would care about all of them, then your life becomes simpler. So you could actually just, let's say you just fill all the unobserved entries, the gray entries, fill them with zeros, and then do SVD. That's what the first approaches were doing in this competition for Netflix. And they turned out to not perform well at all. So, and I don't know if you have any intuition for this, but well, one intuition is because, well, there's just so many gray entries, right? It's 99% of them are gray. So that's, I will just be much too influenced by the gray ones. And what this very nice change was, people found in this competition, is that I should only care about the observed entries. And if I do that, only do this least square error on the observed entries, I get much better predictions. And well, you still get a W and Z matrix, but a much better one, which has much better test accuracy. So test accuracy is measured on a different set of observed entries, which we do not have available for training. Okay, so I'm just saying the omega, the set of observed entries, is really important here. And interestingly, it also has a huge influence on understanding the problem. So yeah, because I told you that people are trying to prove that if we solve this problem, there are no local minima. So, and yeah, if omega is the full set, then this is just very easy. And if omega actually now is a subset, then this becomes very hard to prove. But don't worry, this is not something we're going to do in the lecture. I'm just saying it has quite a big influence on what makes this problem hard or easy. Actually, this problem is NP hard if you want to find the best matrices for omega, even for k equal 1, if you only care about some observed entries. And if omega is every entry, then it's super easy. Then it's just SVD. So from very easy to NP hard by just choosing a different set of observed entries. And we cannot choose the observed entries, right? This is given to us by the data. We have to deal with them. So, okay, that's a bit about the theory of this stuff. But yeah, we're not going to prove anything except that we proved one example is not convex. We proved here f, even the identity function of f is not convex. So I can give you a little second example as a homework, because this is a nice question which came up in the break. And the question was, so yeah, W times Z, that's not convex, but we are squaring the error. We should supposed to be square the error. So what if we do that? What if we take, so f being the square of ZW. That's actually much closer to the real loss function that I told you we care about. So this would be if your observation x is 0, then this is actually the very loss function we defined here, right? So that also answers the question that you rightfully asked, that actually you care about this loss function. So if we do care about that one, then let's try to understand this little homework here. If that case is a convex function. If that squaring fixes this convexity issue or not. That's a very good thought exercise for you. Okay, any comments on this? So sorry, this became a bit of a heavy slide, but I'll upload it and try to write a bit more clearly. Any questions? Then we move on to something a bit easier, namely, well, or more practical. So there are practical issues with this, right? Let's say, okay, we can solve this, or we can set this up, of course. So what is it even doing? Why is it a nice idea? And also how to choose the k. This is the number of columns. So this is the number of latent features, as they're often called. So why are they called latent features? That's because here you see you multiply a row with a column. So this is the the movie row with the user column. This is the two you multiply. So yeah, you have k entries for the movie. That's this part, and you have k entries for the user. So what that means is I find features for every movie. I have this column, so that's the movie features. And for every user, I also have this column of Z transpose. And that's the features for each user. And they get multiplied, and together they form what we think how many stars they would get, 1 to 5. So user features and movie features, that's this this concept. That's just giving another name to these W matrices and Z matrices. So let's try to look at the features we learn. So does it actually work, or what are these optimal entries when I find a good W? So again, this is the movie matrix. So now I will look at my W matrix, and I will look at movie number D. So I get my 10 features. Here are they. So yeah, let's look at them. So it's a bit easier if you would have only 2 features. Then we could visualize this in a plane. If for every movie, so if k equal 2, that will make life much easier. And then, well, the left picture here is a bit what you would kind of like to do, is that you would hope that for every movie it would give it like 2 coordinates, 2 features, which are like interesting aspects of the movie. So here on the vertical horizontal axis we have if it's preferred by male or female customers. So that's one aspect you could think of. Well, it's a bit unclear. We have never gone collect the data, right? The only thing we know is the stars. But if magically we would look at this W matrix now after training, if we would look at that and would see that the 2 entries of each movie make kind of sense, that the vertical axis is here if it's a serious movie or more funny, low-key thing. So that's a possibility that would be kind of nice if this would happen. So this is kind of the ideal situation. It's not going to be what's happening in practice. But this is what such features would be, right? So yeah, if for every movie you get 2 numbers or k numbers, so do they have a meaning? Whatever they are, I can take them, multiply it with a user vector, and then I get how good they match and what the prediction that would be. Okay, let's look at what really happens in reality. And so this again is for k equal 2. And so now we plot all the movies. That means all the rows of my movie matrix, of the W matrix. So I have 20,000 movies, and I have 2 columns. So here are they. It's not all the 20,000, but it's a subset. So on the x and y axis, I have these 2 factors, and this is what would happen if we would only use k equal 2. So you can, I don't know if you know some of these movies or if you can even read it, but it's actually quite nice. It actually groups the movies together which are similar. Remember, this system knows nothing about these movies. The only thing it knows is how many stars did people give. That's all. So yeah, maybe you know some of them, but they are really, I think it's a good kind of grouping, right? When they're close together, then they are actually similar. What we don't know is what these 2 dimensions actually mean, but that's life. I mean, you can look at this space and maybe cluster things. Say if you can interpret that, something you can do. But it's not that we have a precise definition of what does the x-axis mean and what does the y-axis mean. We don't know. But together we know that they will produce good predictions, so they are actually good features. These 2 features which you have, they produce good predictions when we combine them with the user vectors. So that's kind of nice. So this picture was actually obtained by PCA. They actually used a larger k and then did PCA to go back to 2 dimensions. But that's not so important. You will get the same thing actually if you would run the algorithm I showed you with k equal 2. Okay, any questions on this one? So that's kind of nice, but the question remains how to choose a k. So if you choose k very large, we have more parameters. Then you could say you would expect we get better predictions. We get very accurate fit of all these stars if you use a higher k. If it's a very low k, which is here 2, then you would say you will not get very good predictions, but maybe it will generalize better. So we will have again this overfitting problem here. So that's what's written at the very bottom here. So if you choose k too large, then you might overfit, which means you might get all the observed entries correct, but that doesn't mean that you will be any useful on some of the other entries, which are your test entries. So let's think a bit more about this. So can you give me an example where you could get 0 error? So now we talk about given x. Can you tell me some w and z which gets 0 error, which gets all the entries precisely correct? So if the k is very high, you can choose a very high k if you want. What's a simple thing you could do? Even think of you do all the entries, it doesn't matter. Yeah? Exactly, you could, that's what you were saying, is that you can use w equal x, and you could use and z being the identity. So that's what you could do. So, or you could do the opposite thing. You could just say w is my identity matrix and z transpose is my x. So these are valid choices, right? If the k is large enough, then there's so many columns, then I can just put my entire x matrix here. So when does this work? This actually works. Let's say this works if k is bigger than, let's say, both d and n for simplicity. So if this is the case, then you can do that. Let's be clear what the dimensions are. So x is d by n. So then, yeah, the z always needs to be an n matrix, n by k, and w always needs to be a d by k matrix. So yeah, you would choose your w to be the identity of how many movies you have. So, okay, so you can get perfect fit, but of course you will agree with me that these are not going to be useful predictions. So, actually the example I showed you was for omega is all entries, so even then. But, well, the same thing you can do if omega is anything. Even then you can just choose the observed entries you have. There you put x, and the unobserved one, you don't care about it anyway. It's not appearing in the loss, so you can set them to anything, and you will still get 0 loss. So for any omega, you can do this naive example, and this is very bad. This will have very severe overfitting. So you need to choose a good k, and it's the same thing a bit like in k-means. You also needed to choose how many clusters do I want. It's a bit a similar situation here. So here it's the number of features we have to choose, and so but here it's even more clear because we want to choose it. Why? How are we going to choose it? It's like a hyperparameter. So you remember this from regression classification. Just choose your hyperparameters such that you get the best accuracy on the test set, and that's exactly what you should do here. So there's a little bit of a computational aspect. If you choose the k very large, it's also more expensive to compute, but it's actually not such a big difference. So we spoke about overfitting, that's what we get here. And when you talk about overfitting, the next thing to also consider is regularization. And that's something that you can also do for this type of problems. So remember this part here is what we had before, that was the loss. But I can actually, this is my f of the matrix product. So what we do here is we add two terms, and we can again regularize our parameters by introducing a norm. Now, which norm? Well, it's complicated, but in one sense, you want this norm to make your model simple, so you can try different choices, and again, this is again going to be a hyperparameter. Choose the one which works best for your test set. You could choose the 1 norm, you could choose the 2 norm, but here we talk about matrices, remember? So that's why, so here it's actually written Frobenius norm of the W. So yeah, W is this tall matrix, and Z is also a tall matrix. And then you have two regularization parameters which you need to tune. Here they're called lambda of W, lambda of Z. And again, how do you pick them? Such that it's best on the test set. So that's something you can do to reduce overfitting. And the other thing you can do is to reduce the K. So now you have kind of two ways to play against overfitting. So. Okay, what we still haven't discussed is how to actually optimize this, how to train the model with or without regularization. And I indicated this already a bit, that we were just going to run our favorite vanilla algorithm, which is the algorithm that all machine learning is trained with, which is stochastic gradient descent. So yeah, gradient descent here will be quite clear, I guess. Now, what's stochastic gradient descent here? That's a bit strange, because when we saw this, the first time we saw this over data points, right? We had a sum over data points, and then we could train using just one data point. But here we don't have data point vectors. Here we just have an X matrix. So what's the sum structure? We can only run SGD if you have a sum of many functions. And remember what it does is it picks one element of the sum and only uses the gradient of that function. Now, yeah, here is the sum structure. So it turns out our loss function we define also has a sum structure. Namely, it's a sum over all the observed entries. So if you want to give it a name, then you can call this FDN. So these are functions. They take your parameter, and so they take both these matrices, WZ, they take them and map them to, so I write it as, it takes both the matrices and it maps these to a number. So yeah, we have many functions. How many? Just this size of number of observed entries. That's our objective function. So okay, so the concept remains exactly the same. I will pick one of those and I will compute the gradient with respect to the parameters. There are lots of parameters, but I have to take the gradient with respect to all of them. So that's just the definition. I define this to be my small f dn functions. Well, you could also call them L. That makes maybe more sense. So we have a sum. The overall loss function is this, and it's a sum over many individual loss functions. So, okay, and sometimes you might prefer to take the average over them, so be careful when you do stochastic gradient descent. It's very important that you take the average here or the sum. So what you want is that in expectation, and we're just picking one of them, you want that in expectation you get the L. So that's why I would recommend to normalize here, but as long as your gradient is correct in expectation, I don't bother, and whatever is easier for you to optimize. But conceptually it's a sum, and we want to minimize it. We pick one entry of the sum, that's what we have. Now I need to compute the gradient of this one function. So I need to compute gradient with respect to W. At my current point. What is this? This gradient? It's not a vector, it's actually a matrix. Well, just the dimensions of W, which is d by k. Then the second thing we need to compute, so they belong together. The whole gradient is the concatenation of both of these guys, both of these gradients. So the z gradient of the same function. What is this? Well, it has a dimension of z n times k. Okay, that's what we want to compute. So computing the whole thing is a concatenation of two big matrices. Let's not get there, let's just compute one entry of it. That's much simpler. So this you can always do when you have to compute gradients or stochastic gradients. So I have one function which is defined by dn, that's my function, and I want to know the gradient of the first part. So of that guy. So now we have to be a bit careful by the indices, because we've already decided that which function we want to go for, and that function has the name dn, right? So that actually comes from where? From here. So that's one of the observed entries. So one user, one movie, that's the function we talk about. It's how far away, how far off is our recurrent prediction for user D, movie N. The opposite. So movie D, user N. So we talk about that part of the sum. Okay, that's what dn is. Then I should actually give some colors to this. So let's call this entry green. So I have picked one entry of the sum. I want to use the W gradient and the Z gradient. Okay, so now we want to get the W gradient, the yellow one. So I have to decide on one particular position of that I want to get. So I need to choose an entry of W. Which one do you want? All I'm saying is that the name D is already taken. D is fixed. But I'm still asking for a row of W. So that's why we call this D prime here. So D and N are fixed. That's one function we care about. Still, I need to compute this full matrix gradient of W. So that matrix has rows and columns. The rows are called D prime and the columns are called K. So yeah, here it is, the full expression. Gradient with respect to D prime K, that's one entry of my gradient, of the function Dn. That's what we want to compute. And yeah, that's our goal. Do you agree with the goal? Or is it a bit confusing why we have and we have d and d prime, or is it clear? Who wants to have more details on d prime and n? So, okay, so d prime and d. So we have 100 million functions here, which is one per observation we made. So let's fix one user and one movie, which is one such observation. So what we talk about here, and I'll do this in green, is so we pick one of the functions of our sum. So this is movie D, and user N. So that's what we're going to pick. That's the green stuff. So now I have picked one of my functions from the sum, and now I'm asking the gradient of that function. So the gradient of that function is a matrix, no matter which user or movie I've picked, right? It's a matrix. What's the dimension? It's d by k. So here. So I need to compute all of them. I've fixed d and n, but I need to compute all the yellow entries. So that's what's happening here. And each entry has a name of that yellow stuff, and the name of an entry of the yellow stuff is d prime and k. So k is the column, d prime is the row. I'm just saying it because I want to know all the rows and all the columns. I need to compute the whole gradient matrix here. That's why we need two different variable names. So yeah, if that's a bit unclear, don't worry, you can, it's not hard, you can think a little bit more later where. So let's try to compute the whole yellow matrix, and then I will also want to compute the whole Z matrix later, but that's the second step. Let's do the d prime k entry first, and that's, so let me mark this here maybe. I'll give this a different color. Okay, we are getting there. So the green stuff comes from the fixed function, and the purple stuff comes from what entry of the gradient am I interested in. So okay, so what we wrote here is already the solution. So that's the gradient of this one loss function here, which is this part here. So fix dn. So the dn's prediction, that is say 3 stars. So we ask for that user movie dn, how close are we? So that's what we have here. That's the prediction error. So this is the prediction, and x minus it is the prediction error. And x dn, that's 3 stars, right? Because we said that's the data, the ground truth that we observed. Okay, that's the prediction error. And I claim that the gradient with respect to this thing is what I wrote. So let's try to compute this gradient. It depends on the prediction. That's a bit unclear. Let's do that later. But let's differentiate this whole thing, which is the differential of the square times the inner function. So this is the result of this is the inner function times the derivative of this crazy model, which is harder to compute. Okay, so you will certainly agree with me that the derivative of the inner function is this part. So this one. Sorry, that's the the derivative of the whole thing of the square, right? And now I need to compute the derivative of the inner part, and that one I claim is just the other variable. So that's the other part here, the z. So this is the case if we're actually asking what's the entry at that row. The row is called d prime, where if that happens to be the same row that we have chosen to care about, if d prime is equal to d, then it turns out that, so yeah, we see that this prediction here actually depends on the dth row of W and on the nth column of Z transpose. So because it depends on them, the gradient is actually, the prediction error times this Z here, and that's exactly what is this Z nk. That's exactly the column of my movie. So that column is the inner derivative of my loss function, which is written here. Okay, and it also turns out that if it's not the case, if I ask what's my gradient entry here, what's that entry for a row which was not my choice of dn, then the derivative is actually 0. Because the prediction for the d's movie does not depend on the d primes row of my parameters, so they don't influence each other. The derivative is 0. That's why you have these kind of two cases. So then, yeah, this will, maybe you need to recap this again, and actually we'll also give you code for this. That's this week's lab. So you can play with this and implement it in Python, and you will see that, yeah, this is actually the derivative. And it's not hard, right? We are talking about a function which depends on two vectors only. So the vector of my current movie and user, and I want to differentiate this function depending on two vectors. And it's not hard for you to verify that this is the result. So don't worry about this big expression of two matrices. What it is, it's just a d-nth entry, right? So it's really, what it is just two particular vectors. You don't need the whole matrix, right? We only need the W d's row and the Z n column. So that's the expression we have here. So it's not that nasty to compute the differential. And the exact same thing will happen for if you ask about the second part of your gradient, which is also a matrix. If you ask about a particular entry of that matrix, then you will get the same thing. So the first one is the gradient with respect to the movie parameters, and the second matrix is with respect to the user parameters, the Z matrix. These are the gradients. So what's interesting about this is the cost to compute it. So it's very cheap. So we have fixed D and N, one user movie. We ask what's this whole gradient matrix. The answer is, well, it's mostly 0 anyway, except in that one particular row that we actually have the observation. And how expensive is it to compute that row? So the row is the d prime equal d. Well, compute the prediction error. That costs you k. You just form the prediction. Movie vector times user vector costs k. So order k to get the prediction. Then I need to subtract it from my 3 stars and multiply it with the Z matrix. That's a bit strange. Why would you do that? But it's because that is the gradient. So we want to compute the gradient. So the compute cost is only k, which is very, very cheap. Remember, k is 10, even if you have 1 million movies and 1 million users. So this is very efficient. So that's the big advantage of using stochastic gradient descent. And this is actually really the best algorithm to train such models. And it works even if the function is not convex, as we have seen. So we don't have proof that it works, that's open research, but in practice this works amazingly. So, questions? Yeah, let's write the whole update. So I only showed you what is the gradient actually. So the update is you have to now modify both of your variables. So thanks, so the update steps, once you have computed your gradients, they are very simple. So you update the new W, so I call that t plus 1, is the old one, minus the step size, the gradient, right? Minus gamma times the W gradient. And the same for a set. So that's the whole algorithm. It's really 2 lines, which is pretty amazing. So in Python, this will actually be 4 lines. So that's the whole algorithm. And the gradient here, yeah, they are 0 everywhere except in the row you observe. So this, you will actually only update the d's row of your movie matrix and the n's column of your z matrix. Why? Because the others are unchanged. In the others, the gradient is 0. So there's nothing to do. You don't need to touch this whole matrix to make the update. You only need to touch the row d and the row n of the set. So it doesn't matter if you write this d or n here, because everything else is not modified anyway. So it only affects the one of the rows. So this is a bit surprising because the cost here is really order k, which is very, very cheap. So again, n and d, they're a million or a billion. K is 10 or 50. So it's very nice that you can update. You can do an entire step by just paying the cost of k. So just forming the inner product, basically. So that makes this algorithm very efficient. It's also noisy, but because the steps are so cheap, you can do many, many steps. And the fact that it's a bit noisy, which is what stochastic gradient descent is, that turns out it's kind of a nice property when your function is non-convex. But that's also not completely understood yet, and I'm not going to make any formal statements in this course. But there is a follow-up course if you're interested in this. So, if the function is not convex, when you know how to stop, basically the same as in deep learning. You stop when you have good test error. You stop when your budget is expired or when you are happy with the test error. That's the short answer for this. Okay, we're done. I will give you a different algorithm next time. Very briefly, this is easy. You fix one variable, optimize the other. So we will see 2 algorithms for these problems, SGD, and the other one is fix one variable, optimize the other. And that's all about matrix factorization, but I will do this on Thursday.